So let me continue. Leave me. Okay, so let me share my screen. Can you all see? Yeah. Oh, yeah. So thank you all for joining. Today we'll be answering the question of what have I been doing so far in my PhD. So in this thesis, I will present a programming framework for data privacy with accuracy estimations. And in this presentation, I will walk you through the content of the thesis. So to put this work in context, let's start by stating the problem. Yeah. So nowadays, we are constantly sharing personal information that is being used by several parties to learn about users' behavior, improve services, and at the end of the day, make some money. All these data analysis could be really beneficial for society, and learning about the population could lead to changes in policies, the creation of programs to help vulnerable communities, and so on. But we don't want to disclose these statistics at the expense of someone's privacy. So in particular, we want to avoid people observing the statistics and being able to identify someone in particular in the data set. So differential privacy presents a robust way to protect individuals' privacy while learning about the population by adding some calibrated noise, some calibrated random noise to the statistics before the publication. And its compositional nature has inspired the creation of programming frameworks to implement such analyses or queries. And the idea is really simple. So usually have some primitive with known privacy guarantees as building blocks and use composition properties to combine these blocks and create more complex analyses. So the noise that we are adding to the statistics to preserve the privacy will introduce some errors in the response, and analysts would like to keep an eye on these errors to determine the accuracy of the results. So if we want to compute the accuracy of our analysis in a compositional way, we will need to determine a way to calculate the accuracy of the basic blocks and then a way to combine these estimations. So unfortunately, reasoning about accuracy is complex in nature and is less compositional than reasoning about privacy. So it doesn't come as a surprise that most existing tools for differentially private queries lack or have limited support for reasoning about the accuracy of the results. So in this thesis, we address this limitation by building DPella. DPella is a programming language for differentially private data analysis, which also supports a compositional form of reasoning about accuracy. Our framework provides theoretical upper bounds on the error of the analysis and use Taint analysis to detect a statistical independence of the noisy results to improve the estimations of the error. DPella also allows analysts to reason about the trade-off between privacy and accuracy statically, meaning we don't need to run the query, it rather inspects the structure of your queries to compute these quantities. So this thesis is an extended version of the paper accepted in Security and Privacy this year that was created with Alejandro Russo and Marco Gaboardi. So to walk you through the thesis, first I'll be presenting what differential privacy is. Then we will define the accuracy of differentially private queries, followed by checking how do we track independence of the analysis to compute their tighter error estimations. Then I will present DPella's API components, and we will evaluate our tool with some case studies from the literature. Lastly, I will wrap up the presentation with some conclusions. So let's start defining what is differential privacy. Differential privacy is a rigorous mathematical definition of privacy. And to create an intuition of how it works, let's say we have a query queue that counts the number of employees with salaries above 60K given the data set D. A differentially private version of this query will be Q tilde that takes the same database D and executes Q, obtaining the real count, and finally adds the calibrated noise eta to the result. So what do we mean by calibrated noise? Intuitively, we want all our noisy queries to mask the membership of any user in the dataset. So let's say we have a dataset D1 with Alice's, Bob's, and Charlie's information, and we create another dataset D2 without Bob. So differentially private queries should ensure that by looking at its output, one should not be able to know which dataset was used for its execution. So formally, differential privacy guarantees that by obtaining any output X when running Q tilde over a dataset D1 is almost as likely as obtaining the same output when executed over D2. And this is achieved by magnifying the error, masking the membership of the subjects in the data. So the error will be magnified by two factors. The first one considers how sensible the query we're running is to a change of a record in the dataset. And the second one considers how close we want those two probabilities to be. This is determined by the parameter epsilon. So when we have a noisy query Q tilde satisfying this inequality, we call this an epsilon differentially private query. And the parameter epsilon will impose a limit on the privacy loss an individual can incur in as a result of running the noisy query. So as mentioned before, differential privacy is composable. So this is if we have a set of differentially private queries, let's say Q1, Q2 to Qn, then the composition of these queries will also be differentially private. So how do we calculate the privacy of their composition? So the simplest compositional property states that we can calculate this privacy loss as the addition of the privacy losses of their components. So in this sense, we can think of epsilon as a privacy budget that one can spend on a given data before compromising the privacy of the data subjects. So with this property in mind, DPella provides basic building blocks that are grouped as transformations. This is operations that manipulate a given data set, and measurements, which are used to extract information from sensitive data. So all measurements will require the data set from where we want to extract the information, the epsilon to be consumed by the algorithm, and finally it will return a noisy response. So to calibrate the noise in a way that it masks the membership of a person, we will need to quantify how much a data point can change the result of a query. So we will do this quantification in two stages. One is when we are transforming the table. So in DPella, we represent data sets with the type data who has two type variables. STV refers to the stability, and R is the type of the rows of the table. So the stability refers to a quantification of the change of the result when we add or remove a person from the dataset. So similarly, when we talk about a measurement, the result of a measurement can also vary depending if we are adding or removing a data point. So each measurement in DPella has is represented by this type with the sensitivity quantifying this change. So later I will show you how do we use the stability and the sensitivity to magnify or to calibrate the noise of one of these queries. So every query in DPella will take a measurement that will be performed, the epsilon that can be spent, the data from where we want to extract information, and it will construct a DPella computation yielding a noisy value. So in this case, noisy Q is just an internal function. We don't expose this to the users. Instead, we provide constructors such as count, sum, and average that are just partial applications of this function. So additionally to this primitive, DPella provides a function, Additionally to this primitive, DPella provides a function called budget that takes as input a computation or noisy query and statically generates an upper bound of how much privacy budget will be required for its execution. This function provides an early feedback to data analysts about the privacy budget consumption, allowing them to optimize its usage. So it's important to notice that budget will not run the query. It will do a symbolic execution, gathering all the information regarding the budget consumption. And lastly, DPella's interpretation for privacy consists on decreasing the privacy budget of a query, deducting the required budget from its components. So now I've been talking about noise calibration. So how do we actually calibrate the noise? So the noise will depend on the privacy budget, the stability, the accumulated stability of the table from where we want to extract the information, and the sensitivity of the measurement we want to perform. So let's say we have a program that takes two data sets with their respective stability, performs some transformations over the tables, and finally query the table with one of the measurements provided by DPella. So as I said before, each transformation will compute the accumulated stability of the final table, and the measurement has its associated sensitivity with the indicated epsilon provided by the user. Then if we're using the Laplace mechanism, this is if we're sampling noise from the Laplace, our noise will be sampled from the Laplace distribution with mean 0, and the scale will be described by this operation. So observe that the smaller the epsilon here, the bigger the scale will be, meaning that we will need to add more noise to the result in order to mask the membership of the users. So when we scale this, it will provide privacy, but the bigger the noise, then it will degrade the accuracy of the result. So, but what do we mean by accuracy? Let's just start defining what is the accuracy of one of these queries. So the accuracy of a numerical noisy query bounds how far we are from the real value. So more specifically, it states that with probability at least 1 minus beta, the distance between the noisy query Q tilde and Q is less than alpha. We refer to alpha as the error and 1 minus beta as the confidence. To have an intuition of how do we interpret this definition, let's say that after the execution, the noisy query Q tilde returns a value B tilde. Then for a given beta, let's say 0.1, which give us a confidence of 90%, we can compute the error alpha. Once we have this error, we can conclude that with 90% confidence, the real value B falls in the interval determined by the error. So in general, the lower the beta, the higher the confidence, and the bigger the interval will be. So DPella provides a function called accuracy that statically computes the accuracy of a given noisy query. Oh, I missed that, yeah, sorry. So this function we take a query that yields a noisy value, and we use as abstraction the inverse commutative distribution function, which return the theoretical error alpha for a given confidence. So similar to function budget, the primitive accuracy will not execute the query. In order to construct the ICDF of the final result, it will check the ICF of the components, and based on the subqueries and how they get aggregated, it will compute the ICDF of the final result. So all the DPella measurements have a way to generate their ICDF, since it is derived from the tail bound of the distribution from where the noise is being drawn. So at this point, we have the accuracy for the building blocks. But we want to know what will be the accuracy when we combine these noisy values. So in particular, we're interested in computing the accuracy for the addition of a set of noisy queries. A common approach consists in adding the error of all the operands. This is known as the union bound. Although this is just a straightforward approach, the error of the final result increases linearly with respect to the number of subqueries. So at some point, the bound provided by this approach becomes useless. Another question is, can we do better? The answer is yes. We can use a tighter error bound called Chernoff bound if we can guarantee that the values being added are statistically independent. So that's exactly what we want to do in DPella. We want to detect a statistical independence of the noisy values by using Taint analysis. Let me grab some water. So to understand how the Taint analysis work, let's inspect the query total count written in DPella. In this function, we will add some noisy values and return their addition. So first, we perform a measurement. In this case, it's just a noisy count over a data set DS1 using E1 amount of privacy budget. The result is stored in the variable B1. Internally, every time we perform a measurement, the resulting value is encapsulated in the abstract data type value. Value will carry the noisy result together with its ICDF, and a tag used by the Taint analysis indicating that this noise is freshly sampled. We will call this an untainted tag. So now we compute another noisy count that we stored in the variable B2. So finally, we would like to add B1 and B2 and return their addition. But however, in DPella, analysts are not allowed to directly extract the noisy values and compute operations between them. Instead, DPella provides accuracy-aware operators. In this case, we use operator add, which takes as input a list of noisy values and return a noisy value containing their addition, the ICDF of the operation, and a tag indicating if the resulting value is tainted or not. So in this case, the result of the addition is marked as tainted since the noise is not freshly sampled. Instead, it is inferred from B1's and B2's noise. So to determine the ICDF of this addition, DPella checks the tags of the values being added, if they are tainted or not. In our example, T1 and T2 are non-tainted, so it means that our values are statistically independent, so we can compute their ICDF as the minimum between union and Chernoff bound. Later, we will see why we take the minimum between the two. But to see what happens when we have tainted variables, let's say we define a new variable B3 that is computed as 2 times B1. To do so, we use the operator scalar that also returns a noisy value. The result of this operation must be marked as tainted since the noise of this resulting value depends on B1's noise. Now, if we add B1, B2, and B3, the tag of the addition will remain tainted because the noise depends on B1, B2, and B3's noise. But when computing the ICDF, DPella will detect that one of the tags is tainted. So it means that they are not statistically independent, so the ICDF will be computed just using the union bound. Importantly to note here is that the ICDF and the tag of a noisy value can be computed statically, meaning that we don't need to run the query in the database to generate these values. So to compare these two bounds, let's refine our total count query, and now we will perform the noisy count, the addition of noisy count of n noisy counts, right? So in this implementation, we will take as input the privacy budget that we want to spend on each count and the number of noisy count that we want to perform. Then for each A in the range 1 to n, we will store, we will compute their noisy count, and we will add those values and store it in the variable C, and then return this result. So to inspect the error of total count, we call the function accuracy, indicating the total privacy budget, the number of counts, and the confidence level we want. In this case, we are indicating a confidence of 90%. Now, if our operation add wasn't able to detect a statistical independence of the components, the error of the addition will be calculated using the union bound. So we can see that in this case, this error will increase linearly with the number of noisy counts being added. Now, if we keep track of the statistical independence of the noisy counts and the combinator only applies the Chernoff bound, we will produce a tighter error estimation most of the times. So in general, Chernoff bound is asymptotically much better when estimating accuracy, but union bound works best with a reduced number of subqueries. So for this reason, when the values are statistically independent, DPella return the minimum between union and Chernoff bound. So now we have established a programmatic way to reason about the accuracy of our primitive and their composition. So we can finally present all the components of DPella's API. So as mentioned before, we provide primitive for transformations and measurements, but also we dispose to functions for analysis. This is the budget and accuracy function. And we have some accuracy-aware operators to combine noisy results. So how do we use all these tools, all these primitive in an example? So let's say we have information about the trace of packets on a hotspot, and we are interested in computing the distribution of the length of the packets. So we want to compute the CDF, the cumulative density function of the size of packets. The CDF is basically just a cumulative histogram. So an analyst will create a Haskell file, because DPella is written in Haskell, and that will call it just packets. So the first thing we need to do is to import DPella's API for data analysts, which contains all the primitive to build the queries, but does not include any run function. Here, the name analyst LP means that DPella will add noise from the Laplace distribution to the result of the queries. Then we import the schema of the dataset. The schema is a separated file where we have the structure of the tables that are available. This file does not contain any sensitive data, just the name of the tables with their attributes. In this case, we have a table called network with 6 attributes with the respective type. So back to the analyst file, we define our query CDF that takes as input the bins representing the ranges of the histogram, the epsilon to be expanded, and the data set where it will be executed. In this case, we're indicating that DS must have rows of the type network. And we create a DPella computation returning a noisy list of counts. Now, in the implementation, it's fairly simple. The first thing we do is we use select transformation to select the attribute we're interested in. So basically, we're taking the column size of the table and store it in the variable size. Then for each bin, we take all values that are less than the value of the bin, and then we compute a noisy count. The noisy count will spend a fraction of the total budget provided by the user. So in total, we're creating an epsilon differentially private query. So we perform all these counts sequentially and store the counts in the variable count. Finally, we return an accuracy-aware list containing the noisy counts. And for this, we use the operator vector that takes a list of noisy values and return a list and return a noisy list of values. So we have this implementation, and now we want to inspect the accuracy of this query when we vary the value of epsilon, let's say. So now we go to the interpreter, and we write this in the interpreter. So we call function accuracy, stating that we want 10 bins. So we have the list of the bins, and epsilon will be set to 1. We call function simData that creates an empty table with the structure of the network table. And we state that the confidence level we want is 0.09. So in this case, when we run this function, we will get that with probability 95%, the error of our query with epsilon equal to 1 would be plus or minus 53. Now, if we increment the epsilon, let's say to 5, we will introduce less noise, which is reflected in the error. So now we can also check how much budget it is spent in total by this implementation. Using function budget, we will see that since we split the epsilon between the noisy counts, the total epsilon that we spent for 10 bins is 1. However, let's say that the analyst forgot to do this splitting. So when we call, so it means that when we're performing the counts, we are each time spending epsilon. So if we have 10 bins, we are performing 10 noisy counts. So in total, we will spend 10 times the given epsilon. So with these two functions, analysts can inspect their implementation, reason about the trade-off between privacy and accuracy, and optimize their parameters before executing the query. So we proceed to put DPella in context with other results from the literature. So in particular, we implemented several examples from the literature, and we classified in 2 categories. So we have ping-like queries and range queries. So DPella supports ping-like queries naturally, since our privacy primitive follows closely the ones from ping. However, we go a step further and we provide the accuracy bounds of the achieved by the implementations. Then by implementing range queries, this is answering a set of linear queries, we compare DPella's accuracy estimation with the error guarantees provided by Apex and the matrix mechanism technique. So in this case, we show that while DPella's maximum error estimation may be better for simple cases, it does not scale well for more complex linear combinations. So we will see later how do we plan to overcome this issue. Additionally, we want to compare DPella's estimation that are static with estimations that are dynamic. So one way to calculate the error of a query is to compute its empirical error over synthetic data. This is commonly used when dealing with high-dimensional data sets. The idea is to have a data set that represents the sensitive data, but does not disclose any personal information. So then we can run our query several times and inspect the empirical error. So for a particular example, that is the 3-way marginal, we compute the theoretical error provided by our function accuracy, and we compare it with the empirical one obtained by executing the same program on synthetic data. So for this example, the number of queries to be performed will be scaled by the number of attributes in the data set. So this is the number of columns in the data set. So in order to obtain a good estimate of the empirical error, we will need to run several iterations. In this case, we are performing 1,000 iterations by dimension. So since computing the empirical error will require to execute the query several times, while DPella's estimation will only traverse the code once, we can see that the computation power required by DPella is many orders of magnitudes in favor of DPella. Additionally, since DPella's estimations are data independent, our operator accuracy does not need to perform several transformations on the data set to compute the noisy count, while the dynamic approach needs to do so. So this will contribute to the overheads. So the difference between static and dynamic, we don't see it like a competition. We see it as something that can complement each other. So an analyst can use our operator accuracy to tweak the parameters and then do the dynamic analysis to refine the error estimations. But now the question is, how far are DPella's theoretical bounds with respect to the empirical one? And to answer this question, we provide an operator called empiric that will compare DPella's estimation with the empiric error of a query. So this primitive will take as input a DPella computation waiting for its epsilon, the number of iterations, the epsilon, the number of iterations that we want to perform the same query, the epsilon to be used, and a theoretical confidence that will be used by the accuracy primitive. Then this primitive internally will execute the query as many times as indicated, collecting only the noise added in each measurement. So we'll run this just in an empty database. We don't use the real data. So, sorry. So from there, we have the error that it occurs when we run the queries, and then we can calculate the empirical error and return the percentage of empirical errors that are above from the theoretical one. We call this the beta in empirical. So from this operator, we expect that for a given theoretical beta, the empirical one to be, if we run it several times, we expect those empirical ones to be below the theoretical. Otherwise, we will conclude that DPella's estimation is unsound, since we said that we're providing an upper bound of the error, but the error will actually be greater, the actual error will be greater than the bound we are providing. And additionally, we want the empirical beta to be close to the theoretical one, since it will indicate that our estimates are tight. So we run this empiric analysis in the example of three-way marginals. We computed with a theoretical beta of 0.05, so we have a 95% of confidence. And then we compute the empiric error with 1,000 and 10,000 iterations. So here we can see that most of the empirical estimations are below the theoretical one, so it means that DPella is sound. And we also see that when we increase the number of iterations, the estimations tend to stabilize. So in this primitive, analysts can check, with this primitive, analysts can check that the error provided by DPella is good enough for their implementations. So of course, DPella has some limitations, and this will open the door to add some extensions to it. So DPella's biggest limitation is that it does not allow branching on noisy values. This will facilitate accuracy calculations, but restricts the type of analysis that we can perform and that we can implement in DPella. So to overcome this issue, we propose adding common differentially private analyses as black boxes. So we show that this can be done as long as we have a way to compute their ICDF and the resulting value is considered to be tainted. So we did actually implement noisy max using this approach. This approach can also be used to add more refined and sophisticated techniques such as the matrix mechanism, but still we will need to have a way to compute the ICDF in order to add it to DPella. And lastly, there are several works exploring the use of post-processing techniques to boost the accuracy of the analysis. So to this day, DPella does not support this kind of optimizations, since they usually rely on other notions of accuracy. So to extend DPella with other notions of accuracy, we will need to design a compositional theory, and we leave this to future work. So now it's time to wrap up this presentation. So in a nutshell, in my thesis, you can find the introduction of DPella, a programming language for differentially private data analysis. It allows analysts to statically reasoning about privacy, accuracy, and their trade-off. The key features are that the implemented calculus to reason about accuracy via combinators and their composition, together with the use of Taint analysis to detect statistical independence and provide tighter error bounds. Also, this is an extensible tool. We have extended DPella with other notions of differential privacy, such as epsilon delta differential privacy. We have different sources of noise implementing the Laplace and Gauss mechanism. We support other forms of composition, such as advanced composition. And we have added non-compositional primitive as black boxes, as is the case of noisy max. So that's all I have for you today. Thank you all for your attention.
All right. Thank you. Thank you, Elisabet. Yeah. All right. So, yeah, thank you very much. So we break now and we come in 5 minutes. So 4:15. So let's make it sharp, 1:15. Yeah. All right. So, yeah, thank you very much. And I will stop recording this part. Yeah. Thank you.